This is lecture 7. Today, or in this set of videos, we're going to look at with the RISC main memory. This is the first time we've been really looking at main memory, and we're going to look at some of the instructions that work with main memory. So namely, it's memory, so we're going to be reading it and writing it, and kind of exploring some of the typical uses of main memory. So main memory, I'll keep calling it main memory. It's used for two things. One is storing programs and also storing generic data. Now the issue of storing programs is often we call that program memory. Oftentimes in different architectures it's actually a different memory, but for RISC-V, the program memory and just generic data storage is all in the same memory, and I think out of habit I end up calling it main memory. So main memory is just that one memory we have in the RISC-V, and it's used for programs and generic data, and we'll get into that in more depth later in the videos this week. There are other memories on the RISC-V architecture, namely the register file, which is essentially a bunch of registers, which is kind of what memory is anyway, but typical architectures have something called main memory and register files, and the register file is just another way of looking at a RAM type device. It has some extra features that we'll talk about when we get there. So there's also the notion of levels of memory. I don't think we've discussed this before. Generally speaking, in any architecture you have different levels of memory. Now the main memory is one level, and it turns out that register file is another level. So the low levels of memory are considered, I will say, quote, faster. And it doesn't, in this context, it doesn't have to do with access time. It has to do with the amount of useful stuff you can do with the data in that memory. So the RISC-V is set up such that you can only operate on registers. So you can only grind bits on registers. So you can't add values to memory. You first have to put them into registers. And so what we're going to do, if you have to, is grab values from main memory, put it in registers, perform some type of operation on it, put that value back into main memory again, or into data memory. So typically, because you're passing it back and forth between main memory or data memory, it takes longer. It takes extra instructions, and that's essentially slower. Okay, so that the idea is the data in the register file is faster because I can operate directly on it. I don't have to swap it out like I do with the main memory. So essentially any computer system has levels of memory. So for anyone who knows anything about more advanced computer architectures, there's always a notion of cache memory, which is just faster memory, essentially faster memory than something like the hard drive. Okay, as the memory levels go up, usually it gets bigger and it gets slower, and we'll talk more about that later. So this here is the main memory. This memory, as you know, it's holding instructions, but it's also holding data. And what I'm going to be doing is taking data from this other memory here, the register file, and passing it back and forth between these two things as I need to. So this is the main memory. It holds both program memory and data memory. What we're talking about today is going to be primarily the data memory. So in the assembly language or computer architecture, we have the notion of loading and storing, which is essentially the same thing as reading and writing. So when I'm storing something, I am writing it to memory. When I'm loading something, I am reading it from memory. Now in the RISC-V, what happens is when you're storing something, you're storing it from a register into memory. And so in that memory address, in that memory space, whatever is there gets overwritten. So when I'm loading something from memory, I am loading it from memory into a register. Okay, so the idea is the thing in the register gets overwritten, but the data in the memory doesn't. So once again, storing is the same thing as a write operation. Loading is the same thing as a read operation. It's a little bit different vernacular. We use it everywhere. The more you say it and talk about it, the more you'll get used to it, and we'll certainly be using that a lot. So the main memory is kind of strange. It's hard to get used to because it's actually byte addressable. So the notion here is when you're storing something, I'm storing it from a register into memory. So that gives me the ability to store 3 different things without even putting too much effort into it. So I can store bytes into memory, I can store half words into memory, or I can store words into memory. So a byte is a byte, half word is 2 bytes, and a word is 4 bytes. So because memory is byte addressable, I have no problems storing these in memory anywhere I want. It's really operation of from a byte in a register. Will say, I know the registers are 32 bits, but it will take just a byte and store it in a byte in memory. So there's only 3 instructions there, 3 store type instructions, and that's compared to the load. So the load is another issue here. Is for example, we're taking a load byte here. This is a load byte and a load byte unsigned. Okay, so it's going to take a byte from memory and stick it into a 32-bit register. So the question is, what am I going to do with the extra 3 bytes in that register? And the difference is, if I use a load byte instruction, it's going to fill those 3 bytes with a 0. And I already said that wrong. If I use the load byte instruction, it's going to sign extend that byte and fill those extra, 3 bytes or 24 bits with the sign bit of the word that I'm reading from memory. If I load a byte unsigned, it's going to take those extra 3 bytes and fill them with 0. So it's a question of load byte is going to sign extend the other 24 bits, and load byte unsigned is going to 0 extend the other 24 bits in that register when I'm loading a byte. Now it's the same idea for loading half words. If I load a half word unsigned, it 0 extends the other two bytes, so it fills the other 2 bytes with 0. Otherwise, if I use just a load half word as is, it's going to take the MSB of that half word, or the sign bit of that half word, and propagate it through the other 16 bits in that word. Okay, so the idea with load word, it fits directly. I don't really have a choice of doing it signed, unsigned. It's going to take 32 bits from memory and fill that into a register as is. So this is, once again, there's a size issues for when I'm taking something from memory and putting it into a 32-bit register. Not the case with taking a 32 bits and putting it into a 32-bit register, and with the store, it's not even going to be an issue because memory is byte addressable. So memory addressing is something that you should be used to because it is a memory. I have to give it an address. So the thing that's you have to get used to is how the instructions give it an address. And so this is the syntax the instructions, both the load and store instructions use to calculate or generate a address. And essentially it's going to be an absolute address into data memory. So the issue is it's going to take an immediate value, which is referred to as the offset. It's going to add it to the value in some base register, which is essentially a base register value. It's going to add those together to form an absolute address, and it's going to use that address as the memory address that I'm accessing in memory. So once again, the address is formed by the addition of an offset, which is just a constant in the instruction word, and a base register. And the syntax is I put the register name in parentheses and I just stick a immediate value there. So once again, when I'm loading something, this is the register. This is the register I am going to put the value in. Loading something, puts the value from this address into this register. Now for the store, essentially I don't have an example here, but it's very much the same. We'll just get x10, 8, x20. For a store, it's going to take, now there's no comma there either. For store, it's going to take the value in this register and store it at this address. So once again, for a load, I'm taking something at this address and putting it in this register, which is destination register. For stores, this is actually a source register. I'm taking what's in that register and storing it at this address. So these are examples of the load instructions. Once again, there's two different types for bytes and another two different types for half words, depending on whether I'm loading it signed or unsigned. And once again, unsigned, 0 fills the unused bits. Signed, sign extends MSB of the data. So once again, this is really arbitrary, and anytime you're working with any processor, you need to check things out like that. Sometimes they do it quite intuitively, other times they don't. So these are the store instructions, and once again, the syntax is you can see this is written as a source register. It's going to take what's in this register, store it at this address. And once again, the address is a base register plus this immediate value. The syntax is something you need to get used to. We use it quite often. So this is a comparison of these two instructions here. They're very much the same syntax. The only difference is this first operand here. When you're loading something, that first operand, or the leftmost operand, is a destination register, because that's where you're putting the data. And when you're storing something, store instructions don't have a destination register. They have two source registers, meaning it's this thing right here is what I'm going to store at that address in memory. So this is actually a super important slide. The issue is, if registers are so fast and all that stuff, why don't we just use all registers? So there's actually a couple differences here, and the idea here is the register field is a 5-bit. We have 32 registers, so a register represents a 5-bit field in the machine code, so in the underlying instruction format. So if I suddenly have 64 registers, I need 6 bits to encode that. And as I go higher and higher, I need more space to encode the register values, and at some point it just makes the instruction words too long. So the fact that there's 32 registers is kind of a compromise. Lots of RISC processors have about that many. Some more, some less, but 32 is a standard value out here. But more importantly, what's the issue is that with registers, you have to specify a register value when you're working with registers. And so that becomes kind of inflexible. And as you'll see in the problems we do, if I don't have to specify a register value, such as this, the register becomes, I know it looks like a register value in there, but this register value is being used as a base address. It becomes a variable, and it's very flexible in the program. Whereas this instruction here, I'm using the instruction or the register values directly. When I use the register value as an operand in a base address, it's very, very flexible, and we're going to see that quite a bit in the problems we do. So this is another really important slide. There's a couple other, quote, load type instructions that we use quite often. We use these two quite often, particularly this one. And they're not really load instructions. They're actually pseudo instructions that we will actually mention later. It's actually written in the text better than I can explain it here. The idea here is this load immediate. If I need an immediate value, a non-zero immediate value into a register, I use a load immediate value instruction. Okay, so if I need a zero value into a register, I could certainly use an immediate value, but typically I will use the move instruction, which is x0, moving x0 into a register. I will choose this version. It would also work for this. So I load immediate value into a register. I use the load immediate instruction. Later we'll be using a load address instruction, which loads the address of a label into a register. And something that we don't use at all directly is a load upper immediate instruction. This is actually generated by some other popular, it's actually used in this pseudo instruction. So this is actually a pseudo instruction. When I execute this pseudo instruction, it actually uses a load upper immediate instruction, which is something you don't need to worry about. The assembler takes care of that for you. Honestly, I've never used, in all the coding I've done, I've never used directly a load upper immediate instruction. I use this one all the time, so I want you to make sure you understand this one. This one we'll start using a little bit later. This one, I've never even used it. And that's all, folks. This is our diagram once again. This is our register file. Remember, we'll be transferring data back and forth between the register file and the main memory.